So welcome to another laboratory video. This one would be appropriate for a grade 11 chemistry course, a unit on stoichiometry, one dealing with formula stoichiometry in particular. We're going to be determining the empirical formula for a hydrated binary ionic compound. This compound is binary because it's made of two elements, copper and chlorine. Got some here in a vial, so it's a bluish green colored salt. It's powdery inside there. But this binary compound of copper and chlorine also has water molecules associated with it. So within the crystal structure of the salt, there are trapped water molecules. That's why it's a hydrated binary ionic compound. The purpose of the experiment is to determine its chemical formula. So we're going to figure out the subscripts X and Y within the ionic compound, and we're also going to determine the value for Z, the number of water molecules that are associated with each formula unit of the copper chloride salt. Now you know that copper has multiple charges, so we don't really know what this formula is up front. We're going to figure it out by experiment. So I've got an electronic balance set up. We'll zero it. This is a milligram balance. It has 3 decimal places. So we'll zero it. I'll take a crucible. A crucible is a porcelain dish that's designed to heat things strongly. It's a clean and dry crucible. I'm going to put that on the electronic balance, and you can record the initial mass of the crucible. Now for the experiment, I'd like to use about 2 grams of the salt, a little bit more than 2 grams. So I'm looking at that initial mass. I'm going to just tap some of the salt into the crucible until I've got around 2 grams. It doesn't have to be exact. Tapping it in a little bit more. It's good if the salt is a fine powder. It's good if it doesn't really have any clumps in it for the purpose of this experiment. So I think that's pretty close to 2 grams. So you can record that mass, and now you can calculate the mass of the hydrated compound we're using. I've got a support stand set up. Let me just move my balance out of the way. I've got a metal support stand with a clay triangle that's going to hold our crucible, and it's right above a micro burner. So we're using a smaller burner because we want to heat this with a gentle heat. So I've got it a little bit high up. I'm going to be perhaps moving the burner back and forth. Now let me just tilt the crucible towards you a little bit. I'd like you to be able to possibly see the salt. You can see a little bit of it in the crucible. I'm going to turn the gas on and light my burner. Okay, now this particular salt has a relatively low melting point, so I don't want to heat it too strongly. So I'm just going to move my burner back and forth gently. Okay, I'm looking inside the crucible as I'm heating, and I can already see a little bit of a color change occurring. What used to be a blue-green salt is looking more and more greenish inside the crucible. And keep heating, and I'm noticing around the edges as I heat that there's some brown appearing. So it's turning from blue-green to green, and now there's brown color appearing around the edges. Now think about what we're doing by heating. I'm not melting the salt. I'm not heating it strongly enough to melt it, but there were water molecules trapped within the crystal lattice structure. Those water molecules are relatively loosely held within the salt, so as we heat gently, we're driving the water molecules out of the salt. Now sometimes when you use a crucible, you'll put a lid over the top. Because I'm heating gently, I don't have a lid. I'm not worried about the salt spitting out. We also don't want to completely cover the crucible because we'd like the water to escape as we heat. The water that was trapped in that crystal lattice is turning to water vapor, and it is escaping from the crucible. So I'm going to keep heating. Now at this point of the experiment, you definitely want to heat gently. I'm not trying to melt the salt, but I also want to be sure I've driven all the water away. Now sometimes that's hard to tell. You might be having a white colored salt, and when you hydrated salt and when you heat it, it stays white. So it's hard to tell there whether you're really getting rid of all the water. In this particular salt, you might be able to see in the video on the edges that it's turning brown. So I can tell that that brown color is due to the anhydrous version of the salt. Anhydrous, the hydrated salt after it lost its water, is referred to as anhydrous. So I'm going to heat until there's no more evidence of the original blue-green salt until it's completely brown. Okay? Sometimes when students do this experiment, they're a little bit impatient and they want to heat quickly, they want to heat strongly. When they do that, they end up melting the salt. And when it melts, it sticks to the crucible, and it's then going to be difficult in our next step where we have to transfer it to a beaker. So they usually lose some of their product at that point. So right now, there's very little evidence of the original blue-green salt. I can still see a little bit in the center. So I'm going to keep heating until I'm confident that all that water is driven off. So let's reset when that's ready. All right, so I'm going to try to show you what's happening in the crucible. I'll grab the edges with some crucible tongs, and I'll bring that a little bit closer so you can see that. So you might be able to see that the product is brown, but I broke it up a little bit carefully with a metal scoop, and I could see that there's some green salt left underneath that. So although it might have looked like I was finished because only brown was evident, there was still some green salt underneath the surface, so I need to keep heating. So I've just completed the heating. I've turned off the burner. I'll just grab the crucible again and show you what's inside. So you can see the brown powder, and I'm actually quite happy with the way this has turned out. The powder is a nice fine powder. It's not stuck to the crucible, and there's no evidence now of any green or blue inside, so I'm pretty confident we've driven off all of the water, and it's going to be easy to transfer that to a beaker. Now we're going to need to weigh it or mass it so we can determine how much water escaped. But before I can mass it, I need to cool it for two reasons. This electronic balance is pretty expensive, and I don't want to put a hot object on it that could damage the balance. But also a hot object like that crucible warms the air around it, and that warm air rises and kind of lifts the crucible, gives it some buoyancy. So a hot object gets lifted a little bit by the air, and that could affect the mass reading. So we want to always let the object cool until you can hold it comfortably in the palm of your hand, then we'll weigh it. Now how do I know if it's cool enough to weigh it? I'm going to bring my hand close to the crucible like this. If I feel heat, I can feel a little bit of heat right now, I'm not going to touch it. But when I can bring it close and I don't feel heat, then I'll carefully lift the crucible and I'll hold it over the palm of my hand. If I don't feel heat in the palm of my hand, I'll put it in my hand. When I can hold it comfortably in my hand, I can weigh it. If it still feels hot, I haven't touched my hand, then I'll put it back and let it cool some more. So we're going to let it cool, and then we'll weigh it. All right, so I've taken the crucible off of the clay triangle and I placed it on the metal base of the support stand. On the metal base, it cools faster than if you let it sit on that clay triangle, which was quite hot. Don't ever put a hot crucible directly on a bench top, though. It can damage the bench, and some of that can actually stick to the bottom of your crucible, which would ruin your mass. So if you're cooling a hot crucible, put it on the base of the metal support stand. Now, I put my hand near the crucible, and I don't really feel any heat at this point, so I'll gently lift it, and I'll hold it over the palm of my hand like I described earlier. I don't feel any heat coming off, So I'll hold it in my hand. It feels a little bit warm, but it's not burning in any way. So this is cool enough to weigh. So again, there's our brown product without any water left. So that's the anhydrous product. If water escaped as I heated, what do you think this mass will be compared to the mass before we heated? Let's take a look. So you're going to want to record this mass that you see. Remember, the last 3 digits are decimal places on this milligram balance. All right, so there you can record the mass after we've heated, and now you can figure out how much water was in that sample of hydrated salt. So let me put the balance aside. I've got here a 50 milliliter beaker. I'm going to transfer all of that brown copper salt, copper chloride salt, to the beaker. I don't want to spill any. Get it all in there. Now there's a little tiny bit of powder left. That powder probably has a almost negligible mass, but I'm going to add water to the salt in the beaker. So I'm going to add some water and wash that in. But let's take a look at what happens when I add some water. The exact amount of water isn't important, really, but we're going to put about 20 or so milliliters. This is a 50 milliliter beaker, so I'll fill it about a third of the way. So watch what happens as we add the distilled water to our salt. So I'm adding the water, and you can see as soon as I added the distilled water, as it starts to dissolve, you get a bright green colored solution. Remember, the original color of the hydrated salt was a blue-green. So is it surprising that when we add water back, we get a similar color afterwards? All right, let me put that down here. I'll add a bit of water to my crucible, and I'll add that as well, trying to get all of that brown powder into the beaker. All right, so that's about a third full. Pretty sure that's around 20 milliliters. The exact volume, again, is not critical. So we can take a look. It's all dissolved. This salt appears to be highly soluble in water. Now, the next thing I'm going to do is take a piece of aluminum wire. Okay, I've got a thin piece of aluminum wire. I'm going to wrap it around a pen or a pencil to form a coil. You want to form a relatively tight-fitting coil, but not too tight. You want some space left inside. All right, so I'll just adjust that a little bit. Okay, so I've created this coiled aluminum wire. Now, I want to know the mass of my aluminum. So let's put this back in here. You can record the mass of the aluminum. We may, at the end, record the mass again. We'll see how that goes. So let me just adjust the balance so you can see that. So remember, the last 3 digits are decimal places. So this aluminum wire, it's not touching anything around. It's sitting on the pan. You can record the mass of the wire. Again, we may or may not use that later. Let me close the balance. Now I've left this long tail on the aluminum because that's going to go over the edge of the beaker. All right, now I think I'm going to make actually one more coil. I'll put my pen back in there. I'll wrap it around one more time, get a little bit more aluminum in the coil, and I'll compress that a little bit. What I'm going to do is put the aluminum into our solution of copper chloride salt. Now when I put that in, I want the coil to be fully submerged, and then the wire here will hang over the edge. So let me just put a little loop like that. Okay, I'm going to drop that in. And now the coil is submerged. And if you observe carefully, you can see that there's a chemical reaction clearly happening. Okay, there's actually a couple of reactions happening here. One of the things that's happening is there's some kind of gas being produced. that gas is a reaction between the aluminum wire and the water. Surprisingly, it's producing some hydrogen gas. We're not interested in that. So that's a side reaction that we don't care about. But if you look carefully, you can see right there that what used to be silver-colored aluminum wire is starting to look reddish-brown. Okay, so what's going on there? We had some kind of a copper chloride salt, so a salt made of copper and chlorine, and we just added aluminum metal. If you're a chemistry student and you've studied chemical reactions, you might recognize what type of reaction that is, and then you automatically know what that reddish-brown material is. For those of us who haven't studied the chemical reaction types, well, what kind of substance are we familiar with? A metal substance which looks reddish-brown. If you've guessed copper, that's correct. So the aluminum wire is reacting with the dissolved copper chloride salt, and the copper that was dissolved in our salt solution is precipitating. It's precipitating on the surface of the aluminum wire. As the copper precipitates, the aluminum is dissolving, and so we're going to have an aluminum chloride salt. Now you remember that solution was bright greenish blue. That was due to the copper in the solution, the dissolved copper chloride salt. As the copper precipitates, there's less and less copper in the solution. It's precipitating on the wire. As a result, the color of the solution is fading. Right now, it's less green than it was earlier. If I feel the beaker with my hand, it's actually quite hot. Okay, you might be able to see some steam rising even. It's actually very hot. So if it's a very hot solution right now, then you know whether this reaction is exothermic or endothermic. You can think about that. So we're going to leave this. Okay, it's going to have to sit until it's completed. When it's finished reacting, our job then is to isolate the copper that's in there, the copper that precipitated. We're going to separate it, isolate it, and then we're going to dry it and mass it. So then we'll know the mass of copper that was in our copper chloride salt. So let's pause here and we'll reset. So I've let the beaker sit for about 2 or 3 more minutes. Let's take a look to see how things are progressing in there. It's still quite hot. You can see the color of the solution has faded, but there's still a little bit of greenish color to the liquid, telling me that it's not finished. There's still some copper dissolved in that water. But there's a lot of copper that appears to be precipitated. It's quite a thick coating of our aluminum wire. So most of the copper is now precipitated. So I'm going to let this sit overnight. When I come back tomorrow morning, I anticipate the solution above the wire will be completely colorless because all of the copper will have precipitated. So tomorrow morning, our job will be to isolate the copper that has precipitated. All right, so it's the next morning. I'm here early at school to continue our experiment. I've got our beaker here that we left last night reacting. You might be able to see there that the solution is now colorless. There's maybe a little tiny bit of redness to it because there's a little bit of suspended copper metal, but there's no more evidence in the solution of a greenish color, a greenish blue color. So that tells me that all of the copper that was in the solution has now precipitated onto the aluminum wire. Okay, you can still see the aluminum wire hanging there. So what we're going to do today is try to isolate that copper, which means we're going to try to get it out of there on its own. To do that, we're going to do what's called a vacuum filtration. We're going to need, in our filtration, to use a piece of filter paper, and we're going to need to record its mass. So let's take our electronic balance, and you can record for yourself the mass of the filter paper that you see there. Okay, so record that. Remember, this is a milligram balance, so the last 3 decimal places are 0.783 there. All right, so we've massed our filter paper. We'll put our balance away for now. Now, the sink here has a faucet with 2 hoses that I've attached. You might be able to see there, yeah. So I've got a long hose running from the faucet into the drain because we're gonna blast water through there. Now these faucets have little metal side arms. Those are called aspirators. So as the water rushes through that hose, it's gonna create low pressure in the side here. That low pressure is gonna let us do what's called a vacuum filtration. So I attach a thick walled rubber tubing to there. I've got a special flask for the vacuum filtration. It's called a side arm flask. Some people call it a vacuum flask. So it's a normal Erlenmeyer kind of flask, but it has a special glass side arm where we'll attach the rubber hose. I've also got a support stand here with a clamp attached. That clamp is going to hold our flask in place. So I'll put that into the clamp, squeeze it and tighten it. And now we're going to make sure that that's stable, and we'll attach the hose to the side arm. All right, so now the flask is set up with the side arm attached to the hose. I'm gonna grab what's called a Buchner funnel. Okay, you might want to look that up and make sure you understand how to spell it. A Buchner funnel. It's a porcelain funnel. It's a very expensive piece of lab equipment. It's got a bunch of small holes in it like that, and our filter paper will fit inside and lay flat, covering up all of those holes. So I'm going to put that funnel. Now normally when we're not using the funnel, we keep it like this on the bench top. We don't lay it on its side where it could roll off and break. We keep it upside down. I'm going to place it into the flask, just give it a small push. And I'm going to take my filter paper, lay that into the funnel so that all of those holes are covered. I want to wash, just wet the filter paper. So I'm using some distilled water. I'm just going to wet it, dump out the excess water. I'm going to press down to make sure there's no air bubbles in the filter paper. And again, making sure that all of those holes are covered. The filter paper lies perfectly flat. It's not going up the sides of the funnel. And again, put that back on top of the flask. All right, let me just adjust that a bit. So I want you to be able to see what's happening inside the flask a little bit better. Inside the funnel, rather. All right, so we're ready to start filtering. So I'm going to turn the water on. Things are going to get a little bit noisier there. Turn the water on, both the hot and cold water. So now that rushing water is creating low pressure in this hose, which is creating low pressure in our flask. And now air pressure is pushing things through the funnel. That's how vacuum filtration works. So I'm going to take our copper out of the beaker here. I'm going to just lay it for a moment onto the center of my filter paper. Now, when we do this lab at school, my instructions to students are just get the copper off that wire any way you can. So I don't give them any guidelines to that. So there are scoops in our drawers, metal scoops, there's tweezers. What your job is just try to get the copper off the wire, okay? Now there's nothing hazardous here, so I'm not too afraid to touch this, but you might want to wear gloves as you're doing this. All right, so I'm just scraping. At some point that wire is very, very thin. The wire inside where the copper precipitates is very thin because remember, as the copper was precipitating, the aluminum was dissolving. In fact, it's so thin that the copper wire there, the aluminum wire just broke. So I'm going to reach in again, grab the end of my aluminum wire. All right, so I'm just scraping, getting most of the copper off of the wire. Now I'm going to try something. I'm going to make sure I don't lose any. I've been scraping with my metal scoop there. I don't want to lose any of this copper. So I'm going to grab my wash bottle. I'm going to give the wire a bit of a spray, and that seems to help dislodge more of the copper that I wasn't able to scrape off, but there's still a significant amount on the wire, so I'm not done. Keep spraying. Now sometimes the copper sticks to the wire, and so if that happens, in some procedures you might be given some hydrochloric acid to basically wash the wire. The hydrochloric acid would dissolve a bit of the aluminum wire, but not dissolve the copper. So it will help remove the copper from the wire. All right, so I think I've done a pretty good job. I'm gonna show you the copper wire, sorry, the aluminum wire. So I'll just bring that up here. There's my aluminum wire. I don't see any copper left, and I don't have any aluminum in the filter paper. You can see in the video some of our copper on the filter. I'm gonna wash it, because remember, we started, the solution that we originally had was copper chloride. As the aluminum reacted, the copper precipitated out, but the aluminum dissolved into the solution. So in that solution, there should now be aluminum chloride. I don't want any of that aluminum chloride to be on my copper in the filter paper here. So by washing it, I'm removing any aluminum chloride that might be there. I'm doing my best, and it's not 100%, to try to keep the copper away from the edges of the filter paper. All right, as I filter, liquid is going through the funnel. You can't see that in the video, but the liquid that goes through the funnel when you're filtering is called the filtrate. Ideally, the filtrate here would be colorless. There's a tiny, tiny tinge of red in the filtrate here. That tiny tinge of red is telling me that I'm losing a little bit of copper, but it's a very little bit. I don't even think that that amount of copper would matter. All right, now you may notice I just poured the liquid from the beaker into the funnel because there was a bit of copper left in there. But by doing that, I just added a bunch more of that aluminum chloride, so I have to wash again. Not just the copper, I have to wash the entire filter paper. I don't want any of that aluminum chloride to be left on the filter paper. So I'm washing pretty liberally. As you wash, the flask underneath is filling up with the filtrate. As a rule of thumb, you don't want your flask to fill up. If it gets to be about half filled, you should stop filtering, and you might want to empty that filtrate. Now, sometimes when you filter, you're removing something you don't want, and the filtrate is actually the important thing. In our experiment here, the thing we're removing, the copper, is what we want. So for us, the filtrate, the liquid that goes through, doesn't really matter. So now I've washed it. I'm pretty sure there's no more aluminum chloride, but I'm going to do one last thing. That filter paper and the copper right now is wet. It's wet with water that we just washed with. So I've got a bottle here of acetone. Acetone is an organic solvent. Since it used to be used as nail polish remover, it's highly volatile, so it evaporates very, very easily at a low temperature. So what I'm going to do is wash our copper and the filter paper with some acetone. What that'll do is the water that was there will go through, and now the copper and the filter paper will be wet, but they'll be wet with acetone, and acetone evaporates pretty quickly. So what that'll mean is that our filter paper and the copper should dry much faster than they would have if we had just left it wet. Okay? Now some people would put the filter paper with the copper under a heat lamp to help dry it. There's a little bit of a risk there, because if you heat the copper in the open air, it can react with oxygen from the air and turn to black copper oxide. You want to avoid that. So if possible, you want to let it dry slowly, or do what we've just done here. Wash it with something like acetone or maybe an alcohol, which evaporate quickly, and then you'll be able to get a dry sample to weigh a little bit faster. So we're going to let that dry. I'll take the filter paper out of the funnel, and we're going to have to weigh it again. And if you think ahead, we'll then know how much copper was in our original sample of the copper chloride, right? So remember what we've done here? We took a sample of salt that contained copper, chlorine, and water. We first drove the water out by heating it. Then, in the reaction here, we isolated the copper that was in our sample. We know the mass of water, we will know the mass of copper, and so by subtraction, we'll know the mass of chlorine as well that was in our sample that we used. So once we know the mass of copper, the mass of chlorine, and the mass of water, we'll be able to convert those to moles, and then we can figure out the empirical formula of the compound. So we'll stop here and we'll reset, and then we'll weigh our sample. All right, so I've let the filter paper with our copper dry for about an hour in the funnel while I did some other things, and I've taken it out. You can see the funnel right now has nothing in it. I've got all of the copper out of the funnel and the filter paper. That's actually one of the harder things to do without losing anything. Here's our filter paper it's dry, and it's got all of our copper sitting on it. So let's put this on the balance. You can record for yourself the mass of the filter paper with the dry copper. Remember, you know the mass of the filter paper earlier, so you can now figure out the mass of copper. And one last reminder, you know from an earlier piece of data the mass of the sample that we used, which contained copper, chlorine, and water. We now know the mass of copper that was in that sample. We know the mass of water that was in the sample. So then you can figure out the mass of chlorine that was in the sample. Once you've got those masses, you can convert them all to moles. Then you could figure out the empirical formula for our compound. So good luck with your calculations.